Look up tonight. If you're in the northern hemisphere and the sky is clear, you can find Orion in maybe 15 seconds. Belt of 3 stars. Can't miss it. And if you trace a line from that belt up and to the left, you hit a star that is, and I want you to really sit with this, visibly, noticeably red. Not white like most stars. Not bluish. Red. Orange red. The color of something burning low and slow and ancient. That's Betelgeuse, the 10th brightest object in the night sky, the left shoulder of the hunter, and a star that is somewhere between 100,000 and 1,000,000 years away from detonating in one of the most violent events the universe produces. A core collapse supernova. A catastrophic, unscheduled, total structural failure of a star more than 700 times wider than our sun. And here's the thing that has been bothering me since I started going deep on this. You can see it with your naked eye, right now, tonight. A star that is actively dying, visibly unstable, measurably strange, and we cannot tell you when it goes. We cannot even agree on what it's been doing for the last 5 years. Every time we get close to something like a definitive answer about Betelgeuse, the star does something else. Something nobody predicted. Something that forces us to tear up our model and start again. That's not a failure of science. I want to be clear about that right now. But the specific, recursive strangeness of Betelgeuse, the way it keeps being weirder than expected, is genuinely one of the more fascinating stories in modern astrophysics. And it starts with just how enormous this thing actually is. 700 times wider than our sun. Let's make that real, because that number passes through your brain without leaving a mark. Our sun, dropped where Betelgeuse is centered, would extend past Mercury, Venus, Earth, Mars, and reach just to the asteroid belt. Betelgeuse would swallow all of that and keep going, engulfing the orbit of Jupiter, a star so large that if you were standing on Earth with Betelgeuse in the sun's position, you would not see a star in the sky. You would be inside the star. Betelgeuse is also a roiling, violent, unstable object, not a smooth sphere. More like a boiling pot, except the pot is 700 solar radii wide, and the boiling involves convection cells, rising columns of plasma, each one larger than Earth, some larger than the Earth-Sun distance. The star literally brightens and dims in patches. It pulses. It throws material off at hundreds of kilometers per second. It has multiple overlapping cycles, a roughly 400-day pulsation, a longer roughly 2,100-day oscillation. And that longer cycle, specifically, started a genuine argument among astrophysicists that, as of right now, is still not fully resolved. But first, I have to walk you through how supernovae actually work, because the physics matters. A massive star spends its life fusing lighter elements into heavier ones to hold itself up against its own gravity. Hydrogen into helium, helium into carbon, neon, silicon. Each step generates energy. Each step produces a heavier ash that sinks to the core. The star keeps buying itself time until it hits iron. Iron is the most stable nucleus in the universe. You cannot release energy by fusing iron. So when the core fills with iron, fusion stops. The energy source holding the star up for millions of years simply turns off, and what happens next takes less than 1 second. The iron core collapses. Gravity wins instantly. The core, roughly the mass of our sun compressed into a sphere about the size of a city, collapses to nuclear density. The outer layers hit this newly rigid core and bounce. That bounce propagates outward as a shock wave that blows the outer layers of the star into space at roughly 10% the speed of light. The energy released in that fraction of a second is about 10 to the power of 46 joules, roughly 100 times what our sun will emit over its entire 10 billion year lifespan, released in seconds. So, what does this mean for us specifically? The kill zone for a supernova this size is around 25 light-years for severe biological damage, mass extinction territory. The truly dangerous output is the ionizing radiation, the gamma rays, the cosmic ray flux, intense enough to strip planetary atmospheres within that radius. The geological record actually contains iron-60, a radioactive isotope produced in supernovae in sediment layers from an event roughly 2.5 million years ago at about 130 light-years away. Detectable, probably climate-affecting. Not extinction level at that distance, but measurable enough to show up in the rock record millions of years later. Betelgeuse is 650 light-years away, 25 times beyond the severe danger zone. When it goes, it will be visible in daylight, brighter than the full moon for weeks, possibly months. That is real and genuinely extraordinary. But the ionizing radiation will be dispersed enough by the time it reaches us to be negligible. We are safe. Genuinely, specifically safe. And honestly, knowing that makes the story more interesting, not less, because it means we get to watch the whole thing. Now, late 2019. This is where Betelgeuse gets genuinely strange. The star started going dark. Not in the normal sense of its brightness fluctuations, dramatically, measurably darker than ever recorded. By February 2020, it had dropped to about 40% of its normal brightness, visible to the naked eye. Anyone who looked at Orion that winter and knew what they were seeing would have noticed. Betelgeuse was visibly dimmer. The astrophysics community went, and I'm not overstating this, completely sideways. Because one explanation for a red supergiant unexpectedly going dark is that it's about to do something terminal, that the dimming was a precursor to core collapse. Headlines suggested we were about to witness a supernova in real time. Hubble observations traced the cause to an event in September 2019, about 2 months before the deepest dimming. Betelgeuse had ejected a large mass of superheated plasma from its southern hemisphere. That material traveled outward, cooled, and condensed into a cloud of carbon dust that sat between us and part of the star's surface. The southern hemisphere of Betelgeuse went dark because it was behind a dust cloud the star itself had created. And then, in April 2020, the brightness returned to normal. The cloud dispersed. The star had not exploded. It had sneezed, but the return to normal brightness opened more questions than the dimming had. The pre-dimming data showed some photospheric cooling separate from the dust event. The dimming coincided with a specific phase of the longer oscillation cycle in a way suggesting the two things were connected, that the 400-day pulsation had somehow triggered the ejection. That relationship is still an active research question, and it leads directly into the companion problem. If this is the kind of thing that keeps you up at night in the best possible way, hit subscribe. We go exactly this deep every single week. That 2,100-day oscillation cycle had been accepted for decades as the star's own fundamental rhythm, something driven by internal stellar dynamics. And then 2 independent research teams from the Harvard-Smithsonian Center for Astrophysics and the Flatiron Institute's Center for Computational Astrophysics reached the same conclusion almost simultaneously. What if that cycle isn't the star's own rhythm at all? What if Betelgeuse is being tugged back and forth by a companion? Radial velocity data, measurements of whether the star is moving slightly toward us or away from us, showed a signal consistent with an orbiting companion, a smaller object at a few astronomical units pulling Betelgeuse gravitationally in a 2,170-day period that maps almost exactly onto the mysterious long cycle. They called the proposed companion Beetlebuddy. If the long cycle is caused by an orbiting companion, then every model that assumed it was a fundamental mode of the star itself is wrong. The internal dynamics are different. The evolutionary timeline is different. The estimate of how close Betelgeuse is to its final moment, which those internal dynamics were central to calculating, has a different answer. If this is right, the star probably has more time left than some estimates suggested. In 2024, the Gemini North Telescope, an 8.1-meter mirror in Hawaii, with a speckle imager that combines thousands of short exposures to cancel atmospheric blur, was pointed at the predicted position for the companion. Something was there. A point of light at the predicted angular separation, at the predicted position angle. Exactly where Beetlebuddy should be. Honest caveat, this is at the absolute limit of what the instrument can resolve. Confirmation requires more observations. In 2027, the companion should be at its greatest angular separation from Betelgeuse, easiest to see distinctly, and astronomers are already planning for it. The answer is coming, just not yet. And there's an implication that I genuinely cannot stop thinking about. Siwarha, the name given to the companion, likely a red dwarf or subgiant, is orbiting Betelgeuse at a few astronomical units. When Betelgeuse goes supernova, Siwarha will be well inside the lethal radiation zone. The shock wave will hit it directly. A star that has been gravitationally bound to its companion for potentially millions of years, and then the companion detonates and kills it. some extremely dark physics, right? The rotation. In 2017 and 2018, ALMA, the Atacama Large Millimeter Array in Chile, 66 radio telescopes operating as one, produced measurements that appeared to show Betelgeuse rotating at roughly 5 kilometers per second. The technique is standard. You measure the Doppler shift across the star's surface, one limb coming toward you as it rotates, one moving away. Blue shift on one side, red shift on the other. 5 kilometers per second is physically impossible, and I want to be precise about why, because the impossibility is the interesting part. When a star expands from main sequence to red supergiant, angular momentum is conserved, like a spinning skater spreading their arms. As the radius increases dramatically, rotational velocity must drop dramatically, a lot. Calculations put Betelgeuse's expected current rotation at about 0.2 meters per second. ALMA appeared to measure 5 kilometers per second, a discrepancy of roughly 25,000 times. One explanation is stellar cannibalism. At some point, Betelgeuse absorbed a companion star or large planet, depositing angular momentum into its outer layers and spinning them up. Real mechanism happens in other systems. But the more fascinating explanation is turbulence. Remember those convection cells, enormous columns of rising and sinking plasma? Each one is moving. Rising material moves slightly toward us as it climbs. Sinking material moves away. Each one produces a Doppler shift. A research team, including scientists from the Max Planck Institute for Astrophysics, ran simulations of a turbulent stellar surface with Betelgeuse's known properties and generated thousands of simulated ALMA observations. In roughly 90% of those simulations, the turbulent surface looked from the outside like a rotating star, which means ALMA may not have made a mistake. The surface of Betelgeuse may just be so violently turbulent that it produces a signal indistinguishable from rotation. We're not failing to measure rotation. We may be failing to distinguish rotation from extreme convective chaos. And those are very different problems with very different implications.